Okay, so I'm going to begin by talking about a little bit of general chemistry review, and it should be review. These should be things that you are coming into this class with a basic understanding of. You might forget some of the details, but the idea is that this comes back pretty quickly and that we use these concepts throughout the rest of the semester. So I'm going to start with talking about chemical bonds and Lewis structures in this video, just to make sure you have that concept down of what a bond is and what we use Lewis structures for. Okay, so general chemistry review. I'm going to talk about bonds first. And if you remember from general chemistry, there are really two basic types of bonds that we use and we'll see in organic and biochemistry, and those are ionic bonds and covalent bonds. And in general, the way you would identify ionic bonds is almost always they're between a metal and a nonmetal. Okay, so I'm going to put just metal. And typically it's a metal cation and a nonmetal anion. And so remember, cations are positive and anions are negative. And really what an ionic bond is, it's basically oppositely charged, opposite charge ions attracted to one another. And they have opposite charges that are attracted to one another, a positive cation and a negative anion, and so they just are linked together. They're not sharing electrons or anything like that. They're these oppositely charged things that are attracted to one another. Unlike a covalent bond, which is nonmetals basically bonded together, and those nonmetals are sharing electrons. And it's between two atoms. And when we think of how this periodic table is set up, usually you have something way over on the left that's a cation, like a metal, and over on the right that's an anion, a nonmetal. And when you get these nonmetals together, they are typically more electronegative and they want to keep their electrons, so they end up having to share them. But regardless of whether it's an ionic or a covalent bond, you should remember that it always takes energy to break a bond. So if you're going to break a chemical bond, so if you think of these chemical bonds, if you want to break them, it's always an endergonic process. So that means it requires energy to make that happen. Okay. And then if you're going to make a chemical bond, it's always an exergonic process, which means it'll release energy. And that sometimes gets confused for students. People think, oh, you're breaking bonds, you're releasing energy. It's not the case. You release energy when you make new bonds. So if you had something like a hydrogen and you wanted to link it to another hydrogen and make a bond, like H2, you could look up the value for this, and I'm going to use delta H's instead of, this is typically when we're talking about exergonic and endergonic, we're talking about delta G's. When you're just talking about heat, you can think of this as endothermic, meaning heat is required, it comes in, or exothermic, which means heat goes out when it happens. And so when you are taking two atoms and bringing them together, that's actually a negative 436 kilojoules. You don't have to know that number, but you do have to know that that negative means that it's exiting exothermic or exergonic. Energy is released when that happens. okay, when a new bond forms. And then if you were to do the opposite, if you took these two atoms and you separated them into this bond and separated them, that would take energy, and it would be a positive 436 kilojoules. And so that's an endothermic process, because energy is always required to break bonds. So really, one of the best ways to remember this is to think of a diagram of how this takes place. And so if we were to make a graph, and this is going to look a little different than, I'm going to put 0 here, and let's say I put just energy in general, whether it's heat or free energy, and I'll put, so there's 0, this is negative down here, and this is really the distance between the nuclei. If you were to think of it like that, if you had two way far away, so these two atoms that are these hydrogen and this hydrogen that are really far apart from one another, they're not connected, but as they start getting closer, these two nuclei, it goes down in energy. Things get more stable as they get down in energy, because the electrons of this hydrogen, if you think of this as an atom with electrons around it, and this is an atom, a nucleus with electrons around it, this positive nucleus in the middle on both of these is actually attracted to the other's electrons. And when they get closer to one another, they go down in energy. So when you go lower in energy, we consider that more stable. So you get this more stable complex that forms as these nuclei get together. But at some point, when you have these two atoms connected to one another like this, these two sharing electrons, like sharing electrons in between the two plus nuclei, at some point, if you get them too close, these positive nuclei start to repel one another, and it goes back up in energy. Okay, and so really a covalent bond is way down here at the bottom. There's a kind of this just right position where they're sharing their electrons, but they're not too close. And as a result of it, we have, if we go up to these axes, this would be the bond distance or bond length. That's about the distance where they're really happy with one another. And this is the bond energy here. And that means the energy required to break this bond. And I just got done, this would be like on the previous page, I put 436. That would be negative 436 kilojoules down here, because that's what you'd have to put in to make these bonds come apart. So here it's too close. There it is too far apart. And so the only way out of this is to climb out, and that takes energy to do that. So breaking bonds requires energy. So think of it as I've got to kind of walk out of this valley, and that requires energy to break a bond. Okay. So when you think of chemical bonds, remember these covalent bonds, they can be both polar and they can be nonpolar. And this should all sound familiar. When you have a polar bond versus a nonpolar bond, nonpolar means there's equal sharing of electrons in the bond. And this means that there's unequal sharing. And remember, these are bonds, the sharing of the electrons, so polar and nonpolar. And typically what we do is we use electronegativity to figure that out. So if we think of nonpolar molecule, we use this concept of the difference in electronegativity, and we use absolute values to figure this out. So this is the difference in electronegativity. And I'll show you where you get these values. Here in a minute. If we say that if that difference in electronegativity is less than 0.5, we consider that a nonpolar bond. So back in Blackboard, if you're looking at this exam 1 information, if you go down to references, I gave an electronegativity table here, a link to it. And if you look at the differences, these are electronegativities, like fluorine is the most electronegative atom, and then it kind of decreases away from that. If you're looking at nonpolar bonds, It's when you have a less than a negativity difference of 0.5. We consider that nonpolar. But then if you have an electronegativity difference, an absolute value of greater than or equal to 0.5, we consider that a polar bond. Okay, so we'll come back and look at that again here. But if, for instance, hydrogen bonded to hydrogen, if you looked up that electronegativity, it's 2.1 and 2.1. Well, the difference in electronegativity, well, that's pretty easy to do, is 2.1 minus 2.1, or 0.0. So we know that that's a nonpolar bond, okay? But what that threshold is, once you get to 0.5, you know that those atoms aren't sharing those electrons as nicely. So if you had something like hydrogen bonded to fluorine, where this is 4.0 and this is 2.1, well, now the electronegativity difference is, well, 4 minus 2.1. I always put the bigger one so I don't have to think about absolute values, but we know that's a difference of 1.9, so that would be considered a polar bond. And we'll get into how you represent that. Typically what we do is we use that partial negative and partial positive sign, and the partial negative goes on the more electronegative atom because that's where the electrons are shifting towards. And this will come into play as we start to look at more and more functional groups, because in organic chemistry, because when it starts to change the way molecules react depending on if they're polar or not polar. Okay, so that should be some review. Okay, and once we have looked at three-dimensional shapes of molecules, we'll come back to this in the review section. Okay, so that is when you're thinking of normal compounds. That's what we're going to be dealing with, is polar and nonpolar, and then we'll be looking at how these things change and how they react. Okay.